Hello and welcome to another lesson. Today we'll be focusing on how logs are used in radiocarbon dating to determine the age of ancient objects such as fossils and plant matter. Radiocarbon dating is used to measure the time since an ancient object, such as a fossil or plant matter, has been dead through the measuring of the radioactive activity of the object. This is due to the unstable isotope of carbon-14. Carbon-14 is a carbon atom with 8 neutrons rather than the typical 6 of a carbon-12. Carbon-14 is formed in the upper atmosphere by nitrogen-14 being struck by neutrons. This carbon-14 then forms carbon dioxide, which is absorbed by living creatures. Roughly 1 in every million atoms of carbon on Earth are carbon-14. While an object is still alive, it'll absorb carbon dioxide from the air, and this carbon will then become part of the organism. This carbon-14 decays over time, but still has a constant amount retained inside the object as it continues to absorb carbon-14 from the atmosphere. This replenishes the amount of carbon-14 and its associated activity. Each atom of carbon-14 has a half-life of 5,730 years. This means that if you had 1,000 atoms of carbon-14, after 5,730 years, there would now only be 500 atoms of carbon-14, as the other 500 have decayed into nitrogen-14 instead. This nitrogen that is formed is stable, so it does not have an activity, as it does not decay over time. If you know what the activity of an old sample is, and then measure the activity of a new sample that is similar, you can then calculate how much time has passed since the old one stopped absorbing carbon-14 by using logarithms to solve for the time that has passed to get to the activity of the old sample. Now, you're probably wondering what a logarithm is. A logarithm is the inverse of an index, just like how division is the opposite of multiplication. For an index written as a to the x equals y, the corresponding logarithm will be log of base a of y equals x, with the index being what the logarithm is equal to, and the answer of the index is equal to the argument of the log. For example, 3 to the 2 equals 9, so log base 3 of 9 equals 2. Because logarithms are like any other operator in mathematics, they can be added to each side of the equation and still remain equal to each other. This makes it much easier to solve equations using logarithms. In this scenario, the Dead Sea Scrolls, which are thought to be one of the oldest books of the Hebrew Bible, have an activity of 3.97 times 10 to the 4 becquerels, which are the measure of the amount of decays of a substance per second, commonly called the activity. A sample of a similarly prepared scroll has an activity of 4.78 times 10 to the 4 becquerels. Estimate if the age of the Dead Sea Scrolls matches the archaeological age of about 100 AD if the half-life of carbon-14 is 5,730 years. First, we need to list all the values that we've been given. We have the final activity of 3.79 times 10 to the 4 and the initial activity, A0, of 4.78 times 10 to the 4. We also need to find the value for k, the rate constant. This is found through dividing the natural log, ln, of 2 over the half-life of 5,730 years. This equals 1.209 times 10 to the negative 4. Now we write out the decay formula of A equals A0 times e to the negative kt and sub in the values that we wrote down earlier. First, we want to get e on its own, so we divide each side of the equation by 4.78 times 10 to the 4. Now, to bring the t down from the index, we apply a log of base e to each side, so that they are still both equal to each other. This is written as ln for log natural. Here is our first log law. When you have an argument inside of the log with an index, you can bring that out the front of the log and multiply it by the log. This is because if you have a log base 2 of 8, it can be simplified to log base 2 of 2 cubed. We can then remove the index and put it at the front of the logarithm, making it 3 log base 2 of 2. Whenever there is a logarithm with a base equal to the argument, it will always equal 1. So, therefore, to simplify a logarithmic equation, we can move down the index to the front of the logarithm. This allows us to simplify it down. Here we have the natural log of e, which is a log of base e. If you have a base which equals the argument, the power must be 1, as it isn't being multiplied by itself any times. And now we divide each side by the negative 1.209 times 10 to the negative 4 to get a value for t, which we can round to the nearest year. And to check if it matches the year stated in the question, we can subtract the number of years we found it to be from the current year. Therefore, the scrolls are real. The other way that you can estimate the age of an object is through graphing the function of the decay. Here is a plot of the equation we used in the example. It forms an exponential decay with the y-intercept being our initial activity, which is the activity of the fresh sample. This graph can be linearized. Linearization is the changing of the axes to make the plot of the function appear as a straight linear line. This allows for exponential data sets to be displayed linearly, which makes them easier to use. If we zoom in further and change the scale, we can then isolate more clearly the values of the initial and final activity of our samples. If we look at the section above the 10 to the 4, we can see that the grid is not made of squares. This is because each thin line indicates an increase of 1 times 10 to the 4. Then we can move down along the line until the y value is equal to the activity of the old sample, which is 3.97 times 10 to the 4. At this y value, the x value will be equal to the time which has passed since the initial activity. This should give us roughly the same value for time as what we calculated using the equation. To conclude, logarithms are crucial in the process of determining the age of organic samples. This is due to the long half-life of carbon-14, which allows us to calculate how the activity changes over time as the substance decays. Thanks for watching, and have a good day!